All right, today we're pulling back the curtain on the physical world. We're going to uncover the invisible forces that are quite literally holding everything together. We're talking about the secret life of the materials that we rely on every single day. I mean, have you ever really thought about it? How does a massive steel beam just know how to hold its shape under the crushing weight of a skyscraper? Or how do the thin cables of a suspension bridge handle thousands of cars plus wind without just snapping? Well, the secret is that inside every single one of those materials, there's a constant, invisible battle going on. It's this incredible tug of war between the forces trying to pull it apart and the material's own internal strength fighting to hold itself together. So, to understand this battle, we need to learn the language that engineers speak, and that language basically comes down to two words: stress and strain. First up, you've got stress. You know when you pull on a rubber band, that feeling of the band pulling back against your fingers, that resistance, that is like stress. It's the internal force fighting back, measured over a certain area. It's the material literally saying, nope, not today. And of course, what's the result of all that pulling on the rubber band? It stretches, right? That physical change, the amount it deforms, that's strain. It's just a ratio, how much it changed in length compared to its original length, so it doesn't even have units. It's the effect of all that stress. So here's the simplest way to think about it. Stress is the cause. It's the internal fight. And strain is the effect. It's the physical stretch we can actually see and measure. They're basically two sides of the very same coin. Now here's where it gets really cool. When we plot these two things against each other, we can actually map out the entire life story of a material, from the moment a load is applied to the moment it breaks. What you're looking at here is the stress-strain curve for something called mild steel. It's used in, well, almost everything. And you can think of this graph as the material's resume. It tells an engineer everything they could possibly want to know about how it's going to perform under pressure. So the story always begins here, in what's called the elastic region. See how it's a straight line? That basically means the more stress you add, the more strain you get in a really predictable way. But the most important part? If you let go of the force anywhere in this zone, the material snaps right back to its original shape. No permanent damage done. It's perfectly elastic. But if we keep pulling, we hit a super critical moment, the yield point. This is the point of no return. The material has stretched so far that it can't bounce back anymore. From this point on, any change is permanent. Engineers call this plastic deformation. Now, you'd think the material would be weaker now, right? But something absolutely fascinating happens. It enters a phase called strain hardening. The molecules inside get all tangled up, and it actually takes more stress to keep pulling it apart. The material is literally getting stronger, but it's being permanently changed to do it. This hardening process keeps going and going until we reach the very top of the curve. This peak right here is its ultimate tensile strength. This is the absolute maximum stress the material can possibly handle before it starts to fail for real. This is its moment of glory. After hitting that peak performance, the journey is pretty much over. It starts to get thin in one spot, a process called necking, kind of like when you stretch chewing gum too far. And because that area is now smaller, it can't hold the load anymore, and snap, fracture. The end of the story. This whole life story, this curve, it reveals a material's unique personality. How steep that first line is, that's its stiffness. How long the curve stretches out before it breaks, that's its ductility. Think taffy. If the curve was super short, it'd be brittle, like glass. And the total area underneath this whole curve, that represents its toughness, how much energy it can absorb before it finally gives up. So, how do engineers use this dramatic life story to build things that, don't fail? Well, this brings us to probably the most important concept in all of structural design: safety. They do it using something called the factor of safety. It's basically a built-in safety buffer. Think about it. The factor of safety for an elevator cable where failure is just not an option is going to be way higher than the factor of safety for, say, a park bench. It's a promise that we always stay far away from the danger zone. And let me be perfectly clear about this. In the real world, engineers never, ever design a part to operate anywhere close to its ultimate strength. The goal is almost always to keep the working stress safely inside that initial bounce-back elastic region. That way, even under its heaviest ever load, the material is never permanently damaged. Okay, but just when you think you've got this all figured out, there is a massive twist to this story. Because the stress a material feels isn't just about how much weight you put on it, it's also about how fast you put it on. Check this out. If you apply a load nice and slow, the material feels a certain amount of stress. Let's just call it 1 unit of stress. But if you apply that exact same load all at once, you just drop it on there, the maximum stress inside that material is instantly double, 2 times the stress from the exact same weight. Just think about that for a second. And it gets even more mind-blowing with impact. An 80-kilogram weight, that's about 175 pounds, falling just 10 millimeters. That's less than half an inch. That tiny drop multiplies the stress inside the material by a factor of 5.48. A tiny little drop creates this enormous internal force, over 5 times what that same weight would cause just sitting still. This is exactly why a dropped hammer can put a dent in a solid steel beam. So let me just leave you with this question. If a tiny drop, less than half an inch, can multiply the invisible forces inside a material by more than 5 times, how does that change the way you see the world around you? From a car hitting a pothole to a tool falling at a construction site, that hidden battle of stress and strain isn't just constant, it is incredibly dynamic, and it's happening all around us all the time.